So welcome to this recording on optimization, a lecture in a course in Introduction to Symbolic Computation, lecture 32 already. So today we are closing off a chapter, the chapter on plotting and solving equations. So what we are doing today fits rather nicely into this chapter, as we're going to finish off with unconstrained optimization. When one wants to find all global minima, then one has to solve for all the critical points. So we come somehow full circle. In optimization, we distinguish between optimization with constraints and without constraints. With constraints, we can apply the method of Lagrange multipliers, so that's a very general method which we have covered already. Today we look into one very specific type of optimization, polyhedral optimization, and then in a most general way we look at unconstrained optimization. All right, we do this from within a context of symbolic computation, and the second part of this lecture will feature the use of SageMath. So polyhedral optimization is a very specific problem, but at the same time it's extremely widely used. One can see it from the context of geometry. So we have a polyhedron and we have a plane, and we want to find where that plane touches the polyhedron, so that it just touches at a corner or at an edge or at a facet. The plan is to push that plane as far out as possible. We will see this is a very nice way to visualize the simplex method. This is a course in symbolic computation where normal forms played an important role. So there are two different normal forms for optimizing over a polyhedron. So algebraically, the polyhedron is represented by a list of inequalities. In SageMath, we can compute the vertex representation and the H representation of a polyhedron. So algebraically, we work with the inequalities, and we either maximize or minimize. Observe the orientation of the inequalities. With the optimization, we want to optimize somewhere a cost function, and or a profit. We want to typically optimize profit. Geometrically, we want to push a plane as high as possible. In the opposite formulation, we want to minimize costs. And then we want to push the plane as deep down as we can. Now, the two problems seem to be they're definitely related, but they seem to be a little bit at opposite ends. Now, in the polyhedral world, and using the business language, maximizing profit and minimizing costs, they are connected. So if you can solve one problem, you essentially have also solved the other. But that's only in the polyhedral world, of course. One very important method is the simplex method, and here we spent only a little bit touching it. There are entire courses one can spend on linear programming. For us, it's very important that we can formulate the problem and interpret the results. This is a picture that comes from the tutorial from SageMath. I even took the same numbers. We want to maximize x1 plus 5x2, and on the picture, the the target, what we want to optimize, is visualized by the black lines. So in the plane we have a moving line. And we also have what is called a feasible region. So we have two constraints. So we have the red one, the red half plane, that is here defined by this first inequality. And then we have the green half plane defined by this second inequality. There are also the default inequalities. We want positive solutions. So the feasible region F is enclosed by the half planes on the first coordinate sector for x1 and x2, and we have the green constraint. Now, what does the simplex method does? It starts with a solution at one of the corners of the feasible region, here at 0, 0, and then it swaps one of the coordinates for where the maximum, where this black line has a higher value. It will essentially, as we will see, it will first introduce the second variable, because the second variable comes with a higher coefficient. So we follow the geometric intuition. One can also see this problem as a production planning problem, where for every unit of x1, one gets $1 of profit, and for every unit of x2, one gets $5 of profit. We start at a zero production, and we want to introduce the variable that increases our profit most. And that happens by producing values of x2. And we push x2 until we hit one of the constraints. And that's here the constraint drawn by this green half plane. So the simplex method pivots from one corner to the next corner. Okay, so that was the polyhedral optimization. In the unconstrained optimization, we have a surface. That's again the geometric interpretation. What we have given on input is a function of several variables. So I limited the number of variables so that I could still draw the geometric interpretation. So I've picked a sum of squares. So in general, this will not have a unique solution, and we have to be often content with finding a local minimum. The local minimum is here represented by this black dot. In going to SageMath with a three-dimensional plot, I will have the benefit of changing the viewpoint. So which on the slides, I could have made a spin plot, but I didn't do this. So this is one example problem. What are the methods that one can apply? So gradient descent is the method that we will demonstrate in SageMath. So what the gradient descent method does is quite simple. We evaluate the gradient at some point, at the current point where we are, and then we update the current point with a step in that gradient direction. If we want to maximize, we go upwards. If we want to minimize, we go in the opposite direction. We subtract. So the gradient descent method is a very general method, and it all boils down to evaluating derivatives. So for which algorithmic differentiation is extremely useful. Algorithmic differentiation, which we briefly covered in a project in this course, algorithmic differentiation and optimization are often very synonymously, interchangeably used in practice. This is where it all boils down to computationally. To make the connection with the general solvers available in symbolic computation, if we want to find all global optima, so all optima, the minima, the maxima, the saddle points, then we compute all the gradient points by solving the system defined by the gradient. And then we classify the points by the values that we obtain, the values at these critical points in our function. Okay, so this is a very brief introduction to optimization, polyhedral optimization, and unconstrained optimization. Let me switch to the Jupyter notebook, which I have prepared. So I will illustrate the H presentation and the V representation of polyhedra before starting to go into a tutorial that uses the examples that are provided by SageMath. Okay. To make this a little bit dynamic, I will make a new notebook to illustrate that. Also, I'm often fumbling around, and to illustrate step by step the methods that we are seeing. And most importantly, for this course, it is important that we can correctly formulate and interpret the problems. So polyhedra. So polyhedra are defined in two ways, either by the V representation or the H representation. But let me make a random example. So let us look at a polygon generated by 10 random points with integer coordinates between 10 and 99. So to make this polytope look the same, I will set the seed to the date at which this lecture is scheduled. So for 22 July of 22, so a lot of 22s there. So I will generate the coordinates of the x values first with the random element method, where I give as lower bounds the x and the y. So I will do this for 2 this 10 times. So this gives me the values for the x coordinates. So then I will do the same for the y coordinates, copying and pasting. So at the end it will show up like I did a lot of work in one code cell, but that is actually not recommended. So let me execute the same code cell again, and now look at the y values. So the setting of the random seed has the benefit that I will see always the same numbers. Might be boring, but it is predictable. So we have predictable randomness. Then I will make the list of coordinates. So it's a list of lists. So for tuples x and y in the zipped x and y coordinates, the values. And there we see the 10 points. So this is a first introduction to show a little bit the flexibility of Python. So a nice exercise on list comprehensions. Okay, so we are almost there. So now I can define the convex hull via the polyhedron wrapper, where I say that the vertices are defined by the list of randomly generated points. And here is my polygon. So I should have said that a polygon is a polyhedron defined as a convex hull in the plane. So this construction, so perhaps let me indicate. So we are closing towards the end of this course, and this course is the first course on the computational track. In a way, this first section is an invitation to computational geometry. So what we did with polyhedron, we constructed the convex hull, and I will emphasize this. We constructed the convex hull of a list of points. So the convex hull problem is one of the central problems in computational geometry. So this is neatly wrapped with the polyhedron method, or the polyhedron class. Now we can ask for the vertices of this polyhedron with the method vRepresentation. And you see that there are 6 vertices, and I must say that in my opinion they're actually okay. So there are indeed so this is a polygon where with my random choice it looks as if 2 of these points they lie on an edge, so they would not count as vertex points. So this is a nice example actually. So see, if you choose a little bit random numbers, then the decision, so it looks as if this has only 4 corners, but there are 2 points that are seemingly on the not on the corner. So this is interesting. So let me confirm this with the H representation. So the H representation consists of 6 inequalities, and these are the linear equations that define the lines, or these inequalities define the half planes. So interestingly, on the plot we would first think there are only 4 corners, 4 vertices, and 4 edges, but the choice of the numbers has some nearby, or has some almost linear, collinear edges. So typically these would not be counted at first. So when I was looking at this earlier in my preparation, I actually did not see them, but it's good that I see them now. So this is, after all, a very interesting example. So in general, for polygons, if we have 6 vertices, then we have 6 inequalities for every two-dimensional polygon. So notice that I started out with 10 points. So it would be an exercise to adjust the plot and mark the interior points. So in this polyhedron. Okay, so one can do computational geometry in Sage, which we will not do here. We will do optimization. So I will now introduce linear programming. And introduce the example that I had on the slides. So linear programming is optimization subject to constraints. And in order for me to avoid typos, I'm going to copy and paste from my prepared notes. So let me, however, document what I'm going to do. So for an exercise, the type of exercise that you would need to be able to do, maximize the x1 plus 5 times x2 subject to the following constraints. So the first constraint is x1 plus 0.2 x2 less than equal to 4, and the other constraint is, now I have to check again, is 1.5 times x1 plus 3 times x2 less than equal to 4. So I'm formulating this backwards now. I'm looking at the code, and here you see the problem that we're solving. Two linear hyperplanes, and in order for me to be complete, I should actually also indicate that the x1 has to be non-negative and also the x2. So both of them, so these are the two default extra constraints. Okay, so let me define it now. So there is some syntax that needs to be followed, and this is an open book course, so the most important resource for being successful in this course is making your own Jupyter notebooks, so that you can very quickly retrieve what is needed. So you see that we define a problem where we define first that it is a maximization problem. Then we add a new variable, and the new variable is actually the name of a vector. So here the non-negative equals true codifies the what I call the default constraints. Then we have an objective function, what we maximize, and then we can add the constraints one after the other. So in the standard formulation, we have all the inequalities set up as maxima, but there is the flexibility to also have the minima here. Okay, how this is done is another course. It's important that we can interpret the result. So we can solve this and then also get the values for x and y. Oops, get the values for x. There's no x and y here. Okay, so this is a very quick introduction to linear programming as it is wrapped in the SageMath computer algebra system. Okay, so if you have to solve a linear programming problem, then this might be the way to do this. A little bit similar to when I had the linear algebra lecture. If you have to solve a linear system, use the backslash operator. Here you formulate the problem. You can check it. So there are probably selectors as well to show this a little bit better. And then one can solve it. Okay, so what I will illustrate now is how to solve this interactively. So to see the method at work, there is an interactive solver available. For this, we have to convert the problem in a standard form. So you could also essentially see this as an alternative solver. So we give many different ways. So going closer to the matrix vector notation, we start out with the following formulation here. So, and I should be a little bit more careful with the editing. So this is the same problem again, where I have the constraints, but now the constraints are given by numerical data. So the more convenient way to look at this problem is that we see this problem from as defined by matrices and vectors. So here you see the same plot that I showed earlier on the slides. This plot is now justified with the numerical data. So we have the coefficient matrix, the right hand side, the 4, 4, then the cost vector. So where we have 1 and 5 of the coefficients. The symbols that will be used in the interactive problem, it's an optimization problem. Here it is brought in the standard form. So with this way of working, we will have the interactive solver that we can show. And we also have the nice visual representation, but we are limited to a standard form. So there are two types of standard forms. So instead of the max, we have the min, and then typically the constraint type is larger than or 0. Here the variable type indicates the non-negativity constraints. Okay, I spoke about the standard form. So this is the interactive problem defined. Now I will actually convert to the standard form and call this f. Not to be confused, actually. I'm actually confusing this now. I will use SF. So there is the capital F from the picture, which is the feasible region. And you see that it's an LP problem. But if I actually want to see this problem, I have to provide the typeset. So this is a directive that will say that everything has to be formulated or typeset nicely using LaTeX. So again, if you do the view, the PDF will be generated in a popped-up window. So this is more convenient. So this is, by the way, another check for whether you have interpreted the problem here correctly. So this output cell is actually corresponding, is a verification on the correct interpretation of the interactive problem. So where you see now the symbolic format of the problem listed explicitly as the inequalities. The four inequalities, and perhaps I should have said this, that this capital F here, the feasible region, is here defined by its hyperplane representation or the H representation. So you see the inequalities, the four inequalities listed. Okay, so now if we convert, if we are running the simplex method, we start at a corner. So let me run the simplex method. So I will also need to see the nicely typesetted. So I will run the simplex method on the standard form. And then you see all steps executed, one after the other. So it looks involved, and it certainly is if you have to do this by hand, or if you ever took a course where you had to do this by hand. Here it is extremely convenient because you see step after step what happens. So we start indeed with 0, 0, because the value of the objective function is given as 0. And in the terminology of what happens is, in the simplex method, the inequalities are translated into equalities via slack variables. So we started out with x1, x2. We have then the x3 and the x4, which are the added variables to turn the inequalities into equalities. The equalities are called dictionaries. So we have here 3 steps and 3 dictionaries, listing how the variables that are in the basis, so the x3 and the x4 are both 4, and the x1 and the x2 are not in the basis, so they are both 0. So there is this dictionary is a very compact way to show the state in which the problem is in. So we go from 0, 0. We are deciding to put in x2 because x2 has a higher coefficient. So if we are maximizing, we're optimizing the profit. X1 actually goes in, and the variable that leaves is actually the x4. So I was saying this now wrong. So then the variable that comes in is the other variable, x2. So I was using another pivot rule than what is used here. So in these 2 steps, so you can go in this feasible region either going upwards, or you can go, no, actually I said on the slides I said it correctly. So we actually are first in the x1 direction and then we go in the other direction. You could say that, well, why didn't you go immediately upwards? But that has to do with the criteria for which the pivot is being used. So we travel on this polygon, and there are, on a polygon in the plane, there are always two paths. On a polyhedron, it's much more complicated. And for a while, it was an important problem. Does this visit all the corners of the polyhedron? It turns out it doesn't. Okay, that was the second way to solve it. And you see we have again the same solution. So now let us do this step by step, and this might be a little bit cumbersome. So we can enumerate dictionary after dictionary. So in the third fashion, in this third way of solving this, we can work step by step and see what happens for every dictionary of the SF, the problem in standard form. So I will ask for the initial dictionary. So here we have the initial dictionary. And the first thing actually that we look at is what is the basic solution. So the solution is actually 0, 0. It's therefore, it's not going to be, so x1 and x2 are both 0. So the objective value is 0 as well. So we can read this off from the dictionary. Here we can ask now if this is optimal. So I'm doing this in an interactive environment. If you're a programmer, you might think now that you feel an itch. You could now implement your own version of the Simplex algorithm, where the data and all the methods are actually provided already on the dictionary. So I can ask what are the variables in the basic, in the basis. So these are the basic variable. X3 and X4, they are both values 4, and then I can ask for the non-basic variables. So these are the variables that are 0. So there is a value that is entering. So I can ask for the possibilities of the ones that are entering. And I can select this. So let me select this, because based on the choice, I can choose to enter either x1 or x2. I can also indicate, if the first variable enters, what is then the possible leaving variable. So I picked x1 for entering. I could also have picked x1, but if x1 enters, then x4 has to leave. And one can also view this from the dictionary here. Okay, so um, I will say that uh, x4 leaves. I will update the dictionary and look at the dictionary again. So now you see that the value of the value has increased from 0 to 2.6, and the solution, we now have a value, so the d basic variables now contains the x3 and the x1. So the variable that is going to enter now, so if I do this again, the possible entering variables will be, there is no choice anymore, so there's only one choice, so I have to say that the entering value is indeed the variable that I want, the variable that is given. So I entered, then the leaving variable is actually the x1 that is possible for leaving, which is a little bit strange. So if this enters, then what should actually, what I was expecting that would have left would have been the x3, but it's not. If you look now geometrically, so I'm actually finding my optimal point when x2 is 0. So it's kind of unsurprising, but so let me do the final steps. I will update the dictionary with the variables that leaves, and that will give me the optimal solution. Okay, so that is the simplex method solved in 3 different ways. So in the hope that if you ever have to solve a linear programming problem, that you remember at least one. I will conclude this demonstration with unconstrained minimization. And minimizing so copy and pasting again, so which is most likely for me the best thing to do in this presentation in the 5 minutes that I have. What is important here is the aspect ratio. So if I'm tumbling this around, you see that there is one, so there is one valley here, but there is then one peak. So what I do with the aspect ratio, I'm making sure, so the without the aspect ratio changing, this would look like a narrow, tall rectangular cube. I make this more like a true cube by showing this in this way. Now, I formulated this problem as a sum of squares, but you see that if you interpret this as a landscape, there's kind of a valley and then one steep slope, and then one slope that is rather not so steep. Okay, so how do we solve this now? Well, I will apply on this problem the gradient descent method, which is here applied with the minimize method. I have to provide a starting value. If I don't have any starting value, I will choose the origin. And you see that the optimization actually happened really fast. In 10 iterations, it was done. So this will find at best a local optimum. What is often done is that one restarts the minimizer at different random values. So one has several random trials. So the last thing that I want to show is the interpretation. So I will make a plot from the surface and the optimum. And if you look at the instruction, you see that my plot actually doesn't really go through because I made a typo. So now it goes through. So you see that the size of my optimum had to be shown really at 500 pixels, which is a little bit excessive. But you see that the optimum, let me try a little bit more modest ball. And then you see that you can still see it if you know where it is. I didn't first see it. So you see that the interpretation is that we have this valley, but it's almost like there is an entire line that is equally good. So there is a little bit of subtlety here. Okay, so this is the minimization where we evaluate the gradient, and that is also apparent here. So the cost is expressed in the number of gradient evaluations and the number of function evaluations. Okay, with this I conclude this very brief introduction into optimization. Also briefly getting into the H representation and the V representation, which brings us into the world of polyhedra. And we actually solved a computational geometry problem by constructing this convex hull. So there are at least 3 problems in these 3 sections in this lecture. There are also 3 methods for doing linear programming, because that's really the central part of this lecture. Within SageMath, one can ask for a very nice visualization as soon as one has stated the problem, either in this way, or then also in the other way with the dictionary representation. Okay, I hope again that this was an interesting presentation. And this concludes the chapter on solving equations in the course.